Hi, I'm Brian Key, Head of the Brain Growth and Regeneration Lab here at the University of Queensland. I'd like to take you on a tour through my lab, introduce you to my students, my postdocs and my research assistants, and give you a feel of what life in the lab is like.
Come in the morning.
No, I won't set it up then, I'll just leave it till next week.
I know worse.
Yeah, I know what it is, but
I need
it's
you to
definitely
do
not
some
a
stuff
breakfast.
on
No,
yeah.
Really? Whoa.
Will they be fairly concentrated? And I assume that if I add 5 microliters, they'll be okay. Leave it frozen until next week. What do you want me to do?
I'll set up here now on Monday, so...
Well, I can set them up. I can set up the reactions now, and you can take them off when they expire or whatever. It's 12 o'clock. So I can do that now. But I'm not going to purify them. I'm just going to take out a couple of microliters from each and set up a dyscoagulating reaction. And then I'll put them in the freezer and I'll clean them up next week. So can you precipitate them this afternoon and leave them in the freezer until...
No, probably not. Oh no. Did you see my clone? Probably on her way to work while I was doing... Oh! I'm being filmed by my brain.
There are 2 arms to my laboratory. One arm is brain growth and the other arm is regeneration. So for brain growth, embryonic growth in the vertebrate nervous system, and I used 2 model systems for this. I used the zebrafish and the frog xenopus to begin to unravel some of the cues at the molecular and cellular levels that guide axons in establishing the earliest axon tracks in the brain. The philosophy here is that if we can understand how axons grow in the early embryonic brain, if we can understand all the molecular and cellular cues, then we can use this information to help regenerate the nervous system. So the second arm of my lab is interested in regeneration. And to facilitate our understanding of regeneration, I've chosen to study one region of the nervous system which is the most plastic region, and that's the olfactory system. Now the olfactory system is unique. There's a unique set of neurons called the primary sensory olfactory neurons. These have a limited lifespan. Typically our neurons are long-lived. When they die, they're never replenished. However, these neurons, they have a short lifespan of about 30 days. They die, and new primary sensory olfactory neurons are born in the olfactory neuroepithelium and grow axons which extend along the olfactory nerve into the brain. So as I'm speaking, some of my olfactory neurons are dying, but they're being replenished and new axons are growing into the brain to make new functional connections. This is an incredibly plastic system. If we can understand this system, we can understand why the rest of the nervous system is so refractory to regeneration. So we're looking at model systems to understand early growth, and we're looking at model systems to understand regenerating systems.